Welding two spheres on a rod. A slender rod is 80 centimeters long and has mass 0.12 kilograms. A small 0.02 kilogram sphere is welded to one end of the rod, and a small 0.05 kilogram sphere is welded to the other end. The rod, pivoting about a stationary frictionless axis at its center, is held horizontal and released from rest. What is the linear speed of the 0.05 kilogram sphere as it passes through its lowest point? So you can see that this is our rod. This is the center. At a distance L/2 from the center, we have one sphere and we have a bigger sphere on the other end, and this is going to rotate about the center of the rod. Now, before this rotation starts, before it's released, we can look at the initial potential energy of the system. Initial potential energy I call U sub I is going to be equal to mass of the rod times G times capital L/2, because we are at a distance capital L/2 from the bottom, and we have the 0.02 kilogram mass at a distance capital L/2, GL/2, and we have the 0.05 kilogram mass at a distance capital L/2. So the final potential energy will be when the 0.05 kilogram mass passes through its midpoint. So we will have the same potential energy for the rod, mgL/2, with respect to the center, or the center of mass. However, the 0.02 kilogram mass will be at a distance L. So if this is the 0.02 kilogram mass, let's say this will be at a distance L/2 plus L/2, but the other one will be at the bottom with zero potential energy. So the change in the potential energy will be final potential energy minus initial potential energy, 0.02 G capital L minus capital L/2 minus the initial potential energy of the 0.05 kilogram sphere, 0.05 G capital L/2. So this will give us 0.02 minus 0.05 G L/2 as the change in the potential energy of the system. Now we can calculate this. The change in the potential energy is 0.02 minus 0.05 gives us minus 0.03, 9.8 meters per second square. G and L/2 is 0.8 divided by 2. It was a 0.8 meter long rod, 80 centimeters. So this gives us minus 0.1176 joules for the change in the potential energy. Now, if we calculate the moment of inertia of the 0.02 kilogram sphere, it is m1 r1 square. The mass is 0.02 kilograms, and it's a small sphere, so we neglect its dimensions. We treat it as a point. It is at a distance capital L/2 with respect to the center, so capital L/2 square, so that's mr square. This gives us 0.02 times 0.4 square. So that is 0.0032 kilograms meter square for m1, which is 0.02 kilograms. Now the moment of inertia contribution from the 0.05 kilograms sphere will be m2r2 square, which is 0.05 times capital L over 2 square. So that is 0.05 times 0.4 square. That gives us 0.008 kilograms meter square for M2, which is 0.05 kilograms. Now, as for the rod, we need to know the moment of inertia with respect to center of mass axis. That's integral r squared dm. This will be integral from minus L over 2 to plus L over 2 x squared dm. If we are at a distance x, so if we take a mass element at a distance x with respect to the center here, this will have a dm mass, and this is going to give us integral from minus L over 2 to plus L over 2 x squared lambda dx for the mass. Lambda is capital M over L for a uniform rod, and the integral gives us x cubed over 3, which is to be evaluated between minus L over 2 and plus L over 2. So capital M over 3L multiplied with 2 times L cubed over 8. L cubed over 8 minus L cubed over 8 gives us 2 times L cubed over 8, which is ml squared over 12. And if we calculate this, the mass of the rod was 0.12 kilograms. So it is 0.12. The length is 0.8 meters, 0.8 squared, divided by 12. So we find the moment of inertia of the rod 0.0064 kilograms meters square for a rotation axis at the center of mass. Now, if we calculate the change in kinetic energy of the system, that will be final kinetic energy minus initial kinetic energy. The initial kinetic energy was 0 because it was initially at rest, so it is released from rest. So we have the final kinetic energy, which will be purely rotational kinetic energy. That will be 1 over 2 I omega square, where I is the total moment of inertia, the contribution from 0.02 kilogram, from 0.05 kilogram, and the center of mass moment of inertia times omega square. So this will give us 1 over 2 0.0032 plus 0.008 plus 0.0064 omega square, and that gives us 0.0176 divided by 2 omega square. And the change in the mechanical energy of the system in this process is 0. Energy is conserved. Why? Because this is a frictionless axis. Remember that it is rotating about a frictionless axis at its center. So energy conservation applies. Therefore, the change in kinetic energy must be equal to minus the change in potential energy. So we have the change in the kinetic energy. This gives us 0.0088 omega square. So 0.0088 omega square must be equal to minus the change in potential energy, which is 0.1176 joules. And when we calculate the linear speed of the 0.05 kilogram sphere as it passes through the lowest point, the linear speed v is related to angular speed omega, omega times r, omega times capital L over 2. So this will be equal to omega is square root 0.1176 divided by 0.0088 times L over 2, which is 0.8 over 2. that gives us our final answer, 1.46 meters per second for the linear speed of the 0.05 kilogram sphere as it passes through the bottom. Okay, so we have a rod 80 centimeters long, 0.12 kilograms. There are two spheres on the two ends. One is 0.05 kilogram, the other one is 0.02 kilogram. They're welded onto the rod. The rod is pivoting about a frictionless axis at its center. It is held horizontal and then released from rest so that it's going to start rotating like this. We want to know the linear speed of the 0.05 kilogram mass as it passes through the lowest point. Now in this process, we are under the influence of gravitational acceleration g. The gravitational force is conservative, and since there is no friction with respect to this rotation axis, the mechanical energy of the system must be conserved. The initial potential energy is mass of the rod g L over 2. This is the center of mass, distance with respect to the bottom. 0.02 kilogram one is at a distance L over 2, the other one is at a distance L over 2 as well. So final potential energy, because the 0.05 kilogram one is going through the bottom point, it has zero potential energy. The other one is at the top, which is at a distance L over 2 plus L over 2 L. So the change in potential energy is 0.02 g capital L minus L over 2 minus the initial potential energy of the 0.05 kilogram rod. So that gives us a numerical answer. Now, to calculate the final kinetic energy of the system, because the change in kinetic energy is equal to the final kinetic energy, it was released from rest, the final kinetic energy is 1 over 2 I total moment of inertia times omega squared. Omega is the same for all objects, they're welded together. So I have to calculate the moment of inertia contributions from 0.02 kilogram, 0.05 kilogram spheres and the uniform rod. For each of these spheres, which are very small, it's mentioned that they're small, I can use basically discrete moment of inertia formula, sum over I mi ri squared. For m1 it's m1 r1 squared, for m2 it's m2 r2 squared. They are at the same distance with respect to the rotation axis, capital L over 2. And for the moment of inertia with respect to center of mass of a uniform rod, this is a calculation we have done before in the previous problem as well. This is just integral r squared dm, where r is the distance with respect to the rotation axis. So if this is the x-axis and I'm at a distance x, this mass element will have a length L is equal to dx, and lambda times dx is its mass. So dm is equal to lambda times dx. So r squared dm then becomes lambda dx times x squared integrated over all possible x values. So I take this as the origin here. So point P is the origin. So I go from minus L over 2 to plus L over 2 and find the contribution from each mass element. And when we do this integral, we obtain ml squared over 12. So 1 over 2 total moment of inertia omega squared gives us the change in kinetic energy, which according to conservation of mechanical energy must be equal to minus the change in potential energy. This allows us to calculate omega, but the linear speed is omega times r for rotations, so it's going to be omega times L over 2, and that gives us our final result, 1.46 meters per second when reduced to three significant figures.